Techs in Global School, Derivatives. In this class, the concept of derivative and its demonstration are analyzed. Let's start with the proof. Given a curve whose equation is y equal to f of x, the tangent to the curve at a point P given as a comma f of a. Consider a nearby point Q of coordinates x comma f of x, where x is different from a. Using the formula to obtain the slope of a curve seen in analytical geometry, the slope of that curve is f of x minus f of a over x minus a. To transform the secant line PQ to a tangent, bring Q closer to P along the curve, then make x tend to a. So obtain the limit as x tends to a of f of x minus f of a over x minus a. Using the exact same function, we can see that the distance x can also be represented as a plus h. So those same secant coordinates can be expressed as p of coordinates a comma f of a and q of coordinates a plus h comma f of a plus h. Substituting the same coordinates results in a slope of f of a plus h minus f of a over h. And as x tends to a, h gets smaller as it approaches the origin, that is, h tends to 0. So the slope is the limit as h tends to 0 of f of a plus h minus f of a over h. Substituting a with x results in the definition of the derivative as the limit as h tends to 0 of f of x plus h minus f of x over h. This is the definition of the derivative of a function, which can be interpreted as the slope of a function. The derivative of a function can also be interpreted as a rate of change or increase. Using the same function, we can express the delta distance x as the difference between x2 minus x1, and the delta distance y as the difference between f of x2 minus f of x1. When we perform the ratio to get the change between the distances results f of x2 minus f of x1 over x2 minus x1, and when we bring the point Q closer to P to get the tangent, we see that x2 tends to x1, so the instantaneous rate of change is the limit, as x2 tends to x1 of f of x2 minus f of x1 over x2 minus x1. We see that, in the end, it is the same concept with different perspectives. So we conclude that the derivative of a function f with respect to x, denoted as f prime of x, is the limit as h tends to 0 of f of x plus h minus f of x over h. There are several notations to represent the derivative, among which is the Leibniz notation. All of them express the derivative of a function with respect to a variable, in this case with respect to x. We must not be confused and think that they are ratios. They all represent the derivative of a function. In the following diagram, we can see the parts of the derivative of a function. D is the derivative or rate of change, f is the function, and in the quotient, the other d indicates with respect to which variable is to be derived. Then comes the variable to be derived, the limit, and the change in the variable. The change in the variable of the function. Let's look at a first example. A function f is defined as f of x equals x squared minus 3x plus 4. We will get the derivative of the function. We will use the definition demonstrated as it is on the board. As we can see, f of x is already given, so we will get f of x plus h by simply substituting x plus h into f of x. We get x plus h squared minus 3 times x plus h plus 4. Now, substitute both functions into the definition of derivative. Results the limit as h tends to 0 of x plus h squared minus 3 times x plus h plus 4. Minus x squared minus 3 times x plus 4 over h. We expand the numerator using special products and simplify algebraically, obtaining the limit as h tends to 0 of 2x plus h minus 3. In this case, we can apply the laws of limits by separating each addition and subtraction, or we simply send the limit by replacing h equals 0. In this way, we obtain the derivative of the function f prime of x equals 2x minus 3. Graphically, we can see that the original function, because it is quadratic, is a parabola, and its derivative is a straight line. If the slope of f of x is negative, then the graph of f prime of x will be below the x-axis. If the slope of f of x is positive, then the graph of f prime of x will be above the x-axis. All the relative extremes of f of x will become intersections with the x-axis of f prime of x. All inflection points of f of x will become relative extremes of f prime of x. So we can conclude that a function f is differentiable at a if f prime of a exists. And if f is differentiable at a, then f is continuous at a. In this way, also f prime can have derivative denoted as f by prime, and its notation is shown on the board. Let us see an example. We will get the second derivative of the function f of x equal to 2x cubic minus 5x. Using the definition of derivative, define each function f of x and f of x plus h. And we substitute them in the definition obtaining the limit as h tends to 0 of 2 times x plus h cubed minus 5 times x plus h minus 2x cubic minus 5 over h. Developing algebraically using special products and simplifying like terms, we have the limit as h tends to 0 of 6x squared plus 6x, h plus 2h squared minus 5. Sending the limit in, we get 6x squared minus 5. This is the first derivative of the function f of x. To get the second derivative, use the definition of derivative again. So define each function. F prime of x is the one we just got, 6x squared minus 5. And f prime of x plus h is 6x plus h squared minus 5. Substituting and expanding results, the limit as h tends to 0 of 12x plus 6h. And sending the limit results 12x, which is the second derivative of the function f of x. By graphing, we can see the behavior of the three functions. The original function is a cubic, its derivative is a quadratic, and the second derivative is a straight line.
Texan Global School. Global online learning. Knowledge for the world. www.texanglobalschool.com